Name 4 factors that affect
Heat,
heat,
concentration.
and physical state. So now we're ready to look at temperature. Here looks like a first order rate law. First order rate law, because I see nothing here, implied a 1. And then of course this plot says that looks like first order rate law units. So this is the rate constant, and it's temperature dependent, so it's only constant for a given temperature. And we see at higher temperatures, it increases. So if this goes up, rate goes up. So we're going to be talking about the Arrhenius equation. Before we go there, when you increase a temperature of a sample, what happens to its kinetic energy?
It increases.
It increases. So, a gas, we say things are moving around with greater velocity. Liquid as well. Solid, maybe they're vibrating more in place. And so there's probably more collisions. So I've talked about this before. If 2 molecules react, they got to run into each other. If they run into each other with more energy, like they're moving faster, they'll have more energy. It's more likely to break some bonds and form some bonds. So the collision model is based on the kinetic molecular theory. You read about that in the gas chapter a little bit. Molecules must collide to react. And this explains temperature and concentration, both affecting rate. Up to concentration, there's less room. In a crowded elevator, you're more likely to bump elbows with somebody than if there's just 2 of you. 2 of you, you go to separate corners. There's a dozen people in an elevator or subway. We'll come back to that. So here's this thing called orientation factor. I always hate my analogy. If I'm going down Durban Street and somebody's coming down 13th or 12th, I ought to figure out which one it is. The worst accident, I think, would be T-boned, right? T-boned on the driver's side. Maybe the best one would be to be rear-ended. They crumple up the end of my car. So that's my analogy for the orientation factor. The orientation of a molecule during a collision has a profound effect on whether a reaction occurs or not. I get rear-ended, we just exchange insurance. We both drive home. I get T-boned. They call an ambulance, and I got to recover in the hospital, or worse. So here's a collision. This looks like possibly a chlorine, and here looks like nitrogen, oxygen, chlorine maybe. And if this collides like this into the molecules, see they're both moving. The artist implied they're moving. And so here is an effective collision to form Cl2. And so a bond forms there and bond breaks there. And here's our Cl2. And here's our new product. Now if this thing has a little different orientation, slides in this way, it can just bounce back and the molecules just bounce off each other like a gas does. And no reaction has occurred. So we're going to move on to the Arrhenius equation. Be a little bit out of order because here's the Arrhenius equation. Here is that K, our rate constant. And it says here the rate constant is equal to this A times E raised to the negative E sub A RT. So this E sub A is the activation energy. What is the activation energy? It's the amount of energy that a molecule has to overcome or possess for the bonds to break, and it's on a reaction diagram, it's at the top of this hill. So here's energy and reaction pathway going from reactants to products. So here might be like a change in enthalpy.
So activation energy is how much energy a molecule is required to do the reaction, correct?
The energy difference between that of the starting molecules and the highest energy along the reaction pathway is the activation energy. The particular arrangement of the atoms at the top of the barrier is called the activated complex or transition state. So Svante Arrhenius, I talked about him when we talked about electrolytes and freezing point compression. This was the other thing that made him famous. And he suggested that molecules must possess a certain minimum amount of energy in order to react. Molecules are moving too slowly with too little kinetic energy. They merely bounce off one another without reacting. In order to react, colliding molecules must have a total kinetic energy equal to or greater than some minimum value. The minimum value required to initiate a chemical reaction is called the activation energy. And when we simplify things down, we say it's the speed bump on the free energy diagram. Now this fellow noted that for most reactions, the increase in rate with increasing temperature is non-linear. He found that most reaction rate data obeyed an equation based on three factors. The fraction of molecules possessing an energy greater than E sub A, our activation energy, or 2, the number of collisions occurring per second, and 3, the fraction of collisions that have the appropriate orientation. And these three things are all incorporated into this equation. K equals some weird thing here we're calling A, E raised to the activation energy divided by RT. So here's the new thing to talk about, the frequency factor, this uppercase A here. It's a constant or nearly so as temperature is varied, and it's related to the frequency of collisions and probability that the collisions are favorably orientated for the reaction. That's why we looked at the slide and I talked about getting T-boned or rear-ended. Not every collision will produce a reaction. Here's just another look at that slide. Some collisions work, others don't. So how often this occurs is some factor, that letter A in the Arrhenius equation. Alright, one of my favorite topics, reaction mechanisms. What does that mean, a reaction mechanism? It means which bonds are broken and formed during the course of a reaction. When we look at a chemical equation, we're just looking at what we had before and what we have at the end, and there's really no information about how it got there. And a reaction may occur all at once or through several discrete steps. And one discrete step, we give a word, an elementary step. An elementary step is any process that occurs in a single step. Might seem kind of redundant, but we want to be able to apply this first point here. The number of molecules present in an elementary step is the molecularity of that elementary step. And here's three cases we look at: unimolecular, bimolecular, teramolecular. We can have one molecule involved in the elementary step, or we could have two, or we could have three. If you think back on that collision factor slide, there was the single chlorine atom running into the oxygen-nitrogen molecule. So when we have a mechanism that is a series or a sequence of elementary steps, we have these rules. And the first rule is that the elementary steps must add to give the balanced chemical equation. That means we have things like intermediates, things that get produced in one elementary step and get consumed in the next. They go, so you don't see them in the overall chemical equation. An intermediates are species that appear in an elementary step but are neither reactant nor product. Intermediates are formed in one step and consumed in another. And chemists might study these things out and actually detect intermediates in the flask by various means. Why are they in the kinetics chapter? The rate law of the elementary step determine the overall rate law of the reaction. And the rate law of an elementary step is determined by its molecularity. So when we see a reaction and it's first order with just one of the reactants, or maybe we just have a chemical compound and we heat it up and something happens to it, it reacts. And we double the concentration and the rate doubles, we say it's first order. Now, if we doubled the concentration and the rate quadrupled, we would say, well, that molecule has to run into itself. Then we'd call it a bimolecular process. So I told you the other day, 0th order, first order, and second order, that's 99.9% of nature. The reactions outside your body and flask, atmosphere, and ground. Reactions inside living things. So here is an elementary reaction. Now we looked at a multiple choice question, and it said, here's this reaction, the rate law must be, and they had all these things, and you had to select the bottom one that said, rate law can only be determined experimentally, and that is true. So these aren't chemical reactions, they're elementary steps, or it says an elementary reaction. And with that qualifier, what we read in an earlier slide, it said the kinetics must match what's going on here in an elementary step. So this might be like what we just saw with that thing going over the activation energy. It was just a molecule, and if it had enough energy, it kind of broke apart, and that inner side piece rotated around. That would be a unimolecular elementary step, and it would have this rate law. So if I doubled the concentration and the rate did more than doubled, if it quadrupled, I would rule this one out and figure out that it's bimolecular. Because when I doubled concentration, I quadrupled rate. Here, if I doubled concentration, I'd only double rate. So that tells us whether the two molecules have to run into each other for the reaction to occur, or the molecule itself just breaks apart and forms products. So notice we can have bimolecular reaction. This would be two reactants colliding with each other. This would be the same reactant colliding with each other. Same thing down here for the termolecular. We could have an event where three molecules of the same thing have to run into each other in order for the reaction to occur. And here there's two of the one and third of some second thing. And here would be three different chemical species. And notice all of these give you an overall third order reaction. Here's a third order overall reaction. So the overall reaction is the sum of the individual reaction orders. So here's second order and first order. That sums up to 3. First order with C, first order with B, first order with A. That's all going to sum up to third order overall. So rate laws for multiple step mechanisms. Most reactions occur by mechanisms with more than one elementary step. Often one elementary step is much slower than the others, and it's that slow step that gives us the kinetics we observe. The slow step limits the overall reaction rate in Wyoming.
Plenty in Colorado, though.
So here, this one's slow, and this one's fast. This one here, this one's fast, and this one's slow. So here's the rate determining step. Here's a rate determining step. So here's a reaction, NO2 plus CO going to NO plus carbon dioxide. So the researcher goes and maybe does this reaction a few times and varies the initial concentrations and gets this rate law. It means 0th order with carbon monoxide. Double this, the rate quadruples. Double this, has no effect. And that tells us something about how the reaction must be occurring. Now, we possibly need some carbon monoxide for the reaction to occur, but the rate does not depend on its concentration. This might suggest, or does, that the reaction occurs in 2 steps, where 2 NO2s slam into each other, form some NO3 and this NO. And then once you have these species around, it's NO3 reacting with carbon monoxide and going to these products. And so the interesting thing here, if I sum these two things up, let me try it. This thing's going to cancel with this thing. This one can cancel with that one. And now we should see something that looks like this. right? See, this thing is the sum of all the elementary steps. So notice I have NO and CO2 as a product. I had N2O and CO as reactants. Any questions?